All right. Yeah. Most of my classes only have 1 or 2 seniors, but this one is we got 6, I think. So, pretty big chunk. But we're gonna go pretty slow pace. We only have 45 minutes. We're not gonna do a huge amount of new material. Just a quick comment on the reminder here at the bottom, and also just on the test as well. So at the reminder, you can see the spring pendulum lab report is due Thursday for you guys for A-Day, Friday for B-Day classes. So we did it on Thursday. It's due the following Thursday. Today we're going to have a brief discussion about what you came up with. And I know a lot of you are missing your lab partners, but I just want you to look at the graphs that I asked you to put together and kind of compare yours to what I'm going to show here on the slides. And then for the seniors, you guys can see it on the video and compare to what you're coming up with in your lab reports. And then we're going to take some additional notes on simple harmonic motion. Not really, there's not a whole lot. You saw last week, there were just only a few little details. Most was review and just kind of looking at energy and forces and work and all that stuff just from a new kind of perspective, but not a lot of new content. So same today, just a little bit more like that. And then if we have time, we'll look at FRQ number 3 from 2015. That's the goal for today. So let's go ahead and first talk about your graphs. So as you graphed period versus mass and frequency versus mass, what kind of relationships did you see? For period versus mass and frequency versus mass, what kind of, were they linear, nonlinear? What did you find?
Non-linear.
Non-linear, okay. So hopefully when you get your data, and there, obviously is some room for error whenever we're collecting data, especially with stopwatches, there's human reaction time error. And do keep in mind, you don't want to just call it generically human error, but specifically what about the humans made the error. So reaction time on the stopwatch, some of you did video, and so you probably had a little bit better results if you used video, but this is the graph of one group of data from a couple of years ago. We've got time or period on the Y, we've got mass of the spring on the X, and you can see this doesn't look linear, it looks like what sort of relationship?
Square root.
Yeah, it looks more like a square root kind of relationship. And so hopefully you're seeing something like that. Now, when you have a square root relationship, you can do one of 2 things to linearize it. What are your options?
Square root. Or square the x value.
Yeah, you can either, well, right now we see that the y is increasing, but not as fast as the x, right? So we can either square root the x to slow that down, or we can square the y. You can do it either way. And typically speaking, all year long we've said, it's usually better if you don't use square roots. Yeah. But if you look at the formula sheet from College Board, we're gonna see the equation today in just a couple minutes. Down here on the bottom, you see t for period, and it's got equals 1 over f, so we know it's reciprocal to frequency, but then it's got ts for a spring and tp for a pendulum, and both of those equations, I think they're the only 2 on this whole page, yep, both of them do have a radical. And so if we want to kind of mimic what we see on the formula sheet, this one would be a chance where instead of squaring the y, using the square root's actually going to make it look a little bit more like what we see on the periodic or on the list of formulas from College Board. So you can still linearize it either way. So if you've already done the linearization and you squared the y, that's fine. But in terms of seeing it comparatively on the formula sheet, square rooting the x will make it more similar. And then for frequency versus mass, hopefully it's not surprising that it's also not linear, since frequency and period are reciprocal. And so we see this sort of inverse relationship, and we're going to see that it's not just inverse, it's actually inverse and square. So if we look at the equation for the pendulum, for a spring period, we can see that, and this is on the formula sheet, this is the same format you see it. Instead of the whole word spring, they just abbreviate it to S, but it's exactly the same. You can see the T is for period, just like it was in circular motion. So it's the time to make a full rotation or oscillation in this case. And then the 2 pi is, we're going to see today in just a couple minutes, there's a lot of connections to circular motion. If we graphed out the movement of this oscillating spring pendulum, it would look like a sine wave. And so there's that sort of circular, rhythmic, rotational kind of motion. So that's where the 2 pi comes from. And then m is for mass and k is for spring constant. And so we can see that the mass and the spring constant are the two things that actually affect the period. The bigger the mass, what's going to be true about the period? The bigger the period. And hopefully you saw that in your data collection, that the more mass you hung from it, the longer it took for it to oscillate. And then we only checked one spring, so we didn't actually take the time to test multiple springs and see how the spring constant affects it. But that's the way that it fits into the equation. So when you graph your data and linearize it, if you use the square root of the x, you should see this kind of relationship, that the period is going to be proportional to the square root of the mass, like this shows. All right. Now, if we do frequency, since period and frequency are reciprocal, we could say the frequency would be equal to 1 over 2 pi, right? Just take the reciprocal of that, and then multiplied by the square root of k over x, just the reciprocal. So you can use the frequency formula is not on the College Board handout, but you having this one and knowing that they're reciprocal can just easily manipulate it. So if period is 2 pi times square root of m over k, frequency would be 1 over 2 pi times square root of k over m.
Do you think it would be better for us to do like the square root of the mass and the inverse of mass, or just do like one squared and one inverse?
For the frequency?
For the frequency.
Yeah, for the frequency, to linearize it, this is kind of your hint today, if you haven't done linearization yet, that you'll have to, if you want to really make it linear, you'll have to account for both the inverse relationship and the square root. And so, okay, go ahead.
Do you want us to like put it like both on mass, like put the inverse on the mass and the square root on the mass?
If you want it to mimic the equation,
Okay.
then that would be the easiest way. You don't have to do it that way. You
Okay.
could also manipulate the y-axis as well. But if you manipulate the x-axis, it's going to make it more like what we see in the book and on the formula sheet.
Okay.
So yeah, when you do linearization, there's always multiple options, and they can be correct anyway. So I'm not going to grade you wrong for doing it one way over another. But if you just want it to look more like what you'll see in formulas, sheets, and books, then manipulating the x this way is strategic. All right. So note here that g doesn't come into the relationship. How far you stretch it, the amplitude doesn't come into the relationship. It's just based on the mass and the spring constant. So we didn't test a lot of different variables because it was just a little mini lab, just a brief, quick test of how mass compares. But if we did test, like, okay, this time I want to pull it down 5 centimeters every time. Now I'm going to pull it down 8 centimeters every time. Part of the reason we don't test a lot with this is if you go overboard, you can start damaging the springs. If you start stretching it further and further and further, you start damaging the spring eventually. And so we're a little bit limited unless we use a simulation. And so we just keep it real simple for this one. But that's the equation. It is on the formula sheet. It's one that you need to be able to solve for, often in a multiple choice question, asking either to solve for period or mass or spring constant for a given scenario. And so you do have to be really careful. I was working with this equation in my CP class. They don't cover things as in depth as you guys do, but they cover a lot of the same concepts. And the number one mistake is squaring everything first, and it's not that that's wrong, but then they get their order of operations out of order. So my recommendation, if you're solving for m, for instance, divide both sides by 2 pi first, then square both sides, then multiply both sides by k. You do have to follow order of operations, and you can manipulate the order of operations a bit if you're careful and you're clever about the math, but the easiest way is just divide both sides by 2 pi, then square both sides, then multiply both sides by the constant if you're trying to isolate the mass, which is one of the things they'll ask you to do. So just be careful about your order of operations there. All right. And that wraps up springs. I mean, we've spent a lot of time this year talking about them, but that's your last spring-related equation. We had Hooke's law from last semester. This semester we learned the energy equation for springs, the elastic potential energy, and now this is your final one. We're actually getting towards the end of the year where there's not that many more new equations to learn. So that's your last one for springs. Now, it does only apply if the spring is behaving ideally, but that's something you can assume. Usually, the only reason they make this comment here is usually you'll see in the wording of the equation, or the question, I mean, that this spring obeys Hooke's law. And so they're just confirming it is an ideal spring, you can use this equation. They don't always highlight that, but they'll often do it, and I just don't want you to get confused if you read that and wonder, why are they saying that? And it's just to kind of reassure you that you can use all these equations. All right, now I mentioned that simple harmonic motion, it relates a lot to circular motion. We talked a bit about that last Thursday and just wanted to visualize it again today. When we reviewed frequency and period, we saw an animation similar to this with an object moving at a certain pace around a circle. And if we track that circular movement, we can see that the Y position is changing just like a sine wave. And we saw also in the spring pendulum, if you track the movement of the vertical bouncing weight on the spring pendulum, then it also follows this sine wave pattern. The Y value keeps rising and falling and rising and falling. So there is a lot of mathematical connections and a lot of common terminology from uniform circular motion and simple harmonic motion. Just want to make sure that you're not missing that connection. Now, the last concept for simple harmonic motion is the idea of a pendulum. And near the beginning of the year, you did one of your first experiments. It was basically designed to teach you about Toa-Gamma. How do we go about finding relationships graphically and mathematically? It was also designed to get you to learn about linearization. And also just testing different variables. So I don't know how much you remember about that experiment, but you could look back at that one from early in the school year. And we tested things like, how much does the mass affect the period of the pendulum? How much does the length of the string affect the period of the pendulum? How much does the angle that you drop it from affect the period of the pendulum? And we found out that really the mass and the angle, unless you get to real extreme angles, the mass and the angle don't have anything to do with the period of the pendulum, but the length does. And so this equation, also on the College Board formula sheet, they don't use the whole word pendulum, they just abbreviate it with P. But you can see it also has this simple harmonic motion, circular motion relationship. That's why we see that 2 pi coming from. And then we've got the length of the pendulum in meters, and then the acceleration due to gravity or the force field of gravity as G. You can use 9.8 or 10 meters per second squared. All right, so that's the last equation for this unit now. Okay, we are wrapping it up pretty much today. We're not going to do another lab on pendulums just because you did one earlier in the year. I don't feel like we need to repeat that. There's just this one equation, and it's so similar to a spring pendulum, which we spent more time on, that basically if you see it's a pendulum and they're asking about the period, then you know you're going to go to this single equation, the only one that's on the formula sheet with pendulum. Notice that, again, like you learned in that lab way back in this fall, mass doesn't affect it, nor does the amplitude, how far out we pull it or how far up we pull it. Therefore, the angle's not an impact. Although we did discover if you get far up at an angle, it's hard to keep the line tight. And so you get a little bit of slack and then you get a lot more error. But at smaller angles where you don't get that slack in the line error, the period isn't affected by the angle either. And they don't show up in the formula because of that. Sometimes you'll see this mathematically in a multiple choice question. Sometimes you'll see it more conceptually. They might ask a multiple choice question like, which of the following would affect the period of a pendulum? And you have to find, based on looking at the formula, well, it's only really the length and the gravitational force field or the acceleration due to gravity. So those are the things you're looking for. So pretty straightforward. Any questions? We will come back to pendulums a little bit in the last unit. Like I've said before, there's quite a bit of overlap in the last unit to both simple harmonic motion and uniform circular motion, because the last unit's on rotation. And when something is rotating, that can happen in a harmonic way, and it often relates to circular kinds of formulas. So we're going to see quite a bit of overlap. We'll come back to the idea of pendulums and talk about the concept of torque as it relates to this when we're ready for that in the next unit. All right, and We also noted this back in the fall, but there's a little side note here that this formula does become less accurate. There's a larger percent error as you increase the angle because of that slack that accumulates in the line if you try to raise it out too far. It's less so if you have like a metal bar pendulum instead of a string pendulum, because the bar isn't going to have slack in it. All right, so uniform circular motion and simple harmonic motion, lots of crossovers, lots of carryovers, but a few unique formulas here. And these summarize everything. We're, like I said, kind of wrapping up simple harmonic motion today. We've looked at Hooke's law and reviewed that again. We've looked at the concept of frequency being reciprocal to period and reviewed that again. We've defined simple harmonic motion as when the acceleration is directly proportional and opposite to the displacement. We've reviewed that the spring energy, the elastic potential energy equation, is 1/2 kx squared. And then we've just added 2 new equations. So in this unit, there's really only 2 new equations, not a lot of concepts. That's why we can cover it quickly. And so for a spring pendulum or a oscillating spring, it's all based on mass and spring constant. And for a traditional pendulum, or sometimes they're called simple pendulums, it's only reliant on the length of the pendulum and the gravitational force. All right, so there's your nice summary. And that's it for this unit. Like I said, it's really quick. We're going to spend some more time reviewing today and touching on a few example problems and visualizing some things a bit different, but there's nothing else for me to really teach in this unit. Next unit, which we start Thursday for you guys, lot more. So we'll start on the last unit very soon. Tomorrow, since we're pretty much done with this unit, we're just going to review with some practice FRQs. We're going to give you quite a bit of time to work on your test corrections. Again, since the seniors aren't here, I don't want to start that new unit because it is a tough unit. And so we're going to do kind of just practice, review, test corrections. That's our goal for tomorrow's class period. Okay. And so seniors, I don't think I'll record tomorrow if you're watching this video. All we're going to do are some FRQs. You can find those on Axis. We're going to do number 3 from 2015 if we don't have time to get started on that today. And we're going to do number 3 from 2015 and number 5 from 2018 are the 2 that we're going to be working on. But you can find those on Axis if you want to practice those on your own. They're not for an assignment grade, just what we're going to be using for review. And then test correction, just have to find some time to come in and work on those on your own schedule when you're available. All right, so a few other things. Let's jump to this other set of notes here. Just want to review energy a bit more before we wrap things up today. Can we get someone to read this slide for us? Okay, Marco.
Energy in simple harmonic motion. Any oscillating system where the restoring force is proportional to the opposite, negative, of the displacement is in simple harmonic motion, SHM, and is called a simple harmonic oscillator. Also, SHM requires that a system has 2 ways to store energy, and a method that allows the energy to go back and forth between them.
So in a simple harmonic motion system, whether it's a spring scenario, an oscillating spring, spring pendulum, simple pendulum, what are the 2 forms of energy we see being stored in a spring scenario?
Elastic potential and gravitational.
Possibly gravitational if it's vertical, but not always. So it depends on if it's vertically or horizontally oriented. So it might be gravitational. Always is going to be spring, elastic potential, and
Kinetic.
there's going to be movement if it's oscillating, right? So kinetic. So there will always be those 2, possibly gravitational if it's vertically oriented like it was in the lab. But most of the questions are not vertically oriented. Most of them are horizontally oriented. So most of the time you're going to be focusing in on these 2 kinds of energy. The elastic potential energy, 1/2 kx squared, and the kinetic energy, 1/2 mv squared. And what you're going to see in the notes today, it's not about the question that was on your test last time. The test question was about a little spring launcher that shot a ball, not an oscillating system. But a lot of what you're going to see today has overlap mathematically in the energy sense to that FRQ on your most recent test. So if you struggled with that one, you're gonna see some crossover with this. It might help you do the corrections. So this is focused on simple harmonic motion, not a gun situation like that, but a lot of crossover. So if we think about any moment in time while there's a spring oscillating back and forth, the total energy is always going to be the sum of the elastic and kinetic energy. We're talking about a horizontal spring system. So we don't have to worry about the gravitational because it's not changing in height. So that total mechanical energy stays constant. So that was, again, it wasn't simple harmonic motion on that last test, but that first FRQ is all about this concept that you can add up different kinds of energy to get the total mechanical. And if we look at it in oscillation instead of the spring gun like we saw in that FRQ, in an oscillating system, we know that when it's fully compressed, it's all going to be elastic potential. When it's right at the midpoint where the spring is relaxed, it's going to be all kinetic. And then when it's to the other side where it's all stretched, it's going to be all elastic potential again. But if you look at it at some other point, so if we look at it like right here, between the extreme and the midpoint, that's going to be the sum of the two, because the spring won't be relaxed if it's in between, and it will be moving, right? So depending on where we're talking about it, if it's all the way compressed, only elastic. Spring is relaxed and it's right at the equilibrium point, all kinetic. All the way stretched, all elastic again. But here they're marking it here with this X. If it's here, so the picture doesn't quite match, but if it's here, that's when we're going to have a sum of the two. And technically, it's always the sum of the two. It's just that when it's fully compressed, it's not moving, so the kinetic is 0. And when it's in the middle, the spring is relaxed, so the elastic potential is 0. And then when it's fully stretched again, it stops moving. It's got that instant where it has no velocity, so the kinetic is just 0. So technically, it's always the sum of the two. It's just that in the first 3 scenarios, one of the two is always 0. If it's in between those positions, you're going to have literal sum of those two where you have to account for both. The way it looks graphically, last week, we looked at the sort of animation where we saw the bar graphs going up and down. But if we looked at it more as a line graph, we can see that main reason I'm showing you this is I've seen graphs like this quite a bit in the multiple choice portion of the exam over the years. So you'll often see this kind of a shape where you see the total as just a straight line across the top. And you see while the elastic potential energy, the blue line here, is decreasing, the kinetic energy, the green line, is increasing. But if you add them together at any given point, they always add up to the same value. And a key thing, and I noticed this on your test last week on energy, is energy a vector or a scalar? Scalar. So there were a lot of people trying to answer questions as if energy was a vector using X and Y components for energy. X and Y components for momentum, good, because momentum is a vector. But energy is a scalar, so there are no components. So it makes analysis mathematically quite a bit easier. If they give you a graph here and ask you for the amount of energy at any given point in time, you know that they have to sum up to the total. So even if they only give you one of these two graphs and ask you about the one that's not pictured, you know that they have to add up to the total. They have to add up to whatever this peak reaches. So they could not give you the red line and not give you the blue line and only give you the green one. And you could tell what the total is because it's going to be the peak. And you could always, at any given point in time, predict what the elastic would be because it has to be the peak minus whatever the kinetic is at that point. So they wouldn't have to show you all 3 of these energies in a single graphic. You could still interpret it if you understand the pattern. So here we're looking at the beginning. They've got these blue dots here, kind of at time 0, so to speak. The elastic potential energy is maximum, kinetic energy is 0, total energy is constant. If we go forward and look at it here, now that blue dots are here, where elastic potential energy is 0 down here and the kinetic is maximum, but the total is still the same. And then if we look at it at the other extreme, where the elastic potential energy is back to maximum and the kinetic energy is back to 0, but again, the total stays constant. All right, so that's just an important thing to keep in mind as you're answering a wide variety of questions about any sort of energy relationship, in this case focused on simple harmonic motion of springs. So let's practice a couple questions, make sure you're getting the ideas here. So at what location is the kinetic energy of a mass spring system the maximum? Is it at the positive amplitude, negative amplitude, zero, or both of the amplitudes? Where is the kinetic energy maximum? Blake?
At B.
B, correct. When it's at the equilibrium position, the spring is relaxed, so there is no elastic potential energy, but that's when it would be moving the fastest, right? The spring has finished pushing or pulling, and it hasn't started resisting in the other direction yet. Yeah.
So, what would be the one, you showed like 4, and you said how there would, like, the 0 would be for all of them, and then on the last one, they would be added together?
Oh, this one here?
Yeah, for number 4, how would you show that in x equals something?
And x equals something?
Cause like, it just said like x equals negative a, x equals 0, x.
Oh,
So what would the x be for this one?
I see what you're saying. So if, here it wouldn't be maximum of either. Is that what you're asking?
Yeah, but like, what would the x be?
The x is just some position. So they're just showing it's not at equilibrium. It's not at the amplitude, so they would just call it x. So they would, like, here it's 0, here it's amplitude, here it's just some random value. Yeah, it could be any number, yeah. So that's just x, no specific value, no specific label for it. Does that make sense? Okay. All right, next question. At which location or locations is the spring's potential energy maximum? Andrew? D. At the far extremes where the amplitude is greatest in the positive and negative directions, that's when it's going to have all that compression, all that stretching energy stored. At which location is the kinetic energy minimum? Josiah? D. At those extremes again, it's coming to rest just in that instant when it reaches the amplitude. So no movement, no velocity, no kinetic energy. And finally, at which location is the total energy of a mass spring system a maximum? Yeah, it's constant, right? The total stays constant as long as there's no dissipated energy, as long as there's no friction or anything. And there were not too many, but there were a couple of students that on one of the test questions last week tried to involve air resistance. Keep in mind that on the College Board hand, I know this is the old one, but this part's the same on the new one. It says right here, assume air resistance is negligible unless otherwise stated. So if they're asking you to explain a scenario, but they tell you air resistance is negligible, or they just don't say anything about it, you should assume it's negligible. That's sort of a standard that they just expect you to think through all the time. All right, let's see, we get done at 15, right? Let's try a couple more practice problems and but more with the math side of it. So this is just looking at a particular scenario. We know that since the total mechanical energy has to be conserved for a closed system, if we have 2 given points in time of an oscillating spring, we could say that at any point, the elastic potential energy plus the kinetic would give us the total. And at any other point in time, the elastic plus the kinetic would still give us the same total, right? According to those graphs that we saw, the total has to be the same at any given point in time if there's no dissipated energy, if you've got a closed, isolated system. All right? So if we're all the way out at the amplitude, this 1/2 mv squared is 0. If we're right at the midpoint, the elastic potential energy is 0. But at any other position, any other x position, you have to factor all of those in. All right, so let's see if we can solve a couple here. What is the total energy of a mass spring system if the mass is 2 kilograms, the spring constant is 200 newtons per meter, and the amplitude of oscillation is 3 meters? Any ideas on how we could go about solving this one, even just conceptually? Yeah, Andrew?
Just the spring constant. I mean, use the spring energy formula, which is the 1/2 kx squared.
Okay, good. So help us understand though, just to make sure we're not confusing anybody. It says total energy, so why can you just use the spring energy?
Because it tells you the amplitude of the oscillation and the spring constant. Therefore, if the total energy was stored in the spring, that would be like the highest amount of energy that could be stored in it. And then
Right.
there would be zero kinetic energy when that happens.
Good. So if we go back to this relationship, we're saying if it's at the amplitude, this 1/2 mv squared is 0. And so all of the energy is elastic. So if we can find the elastic energy at the amplitude, that is the total energy, because at that point, kinetic would be 0. And so just like Andrew indicated, we can use the 1/2 kx squared. They give us the k value. They give us the displacement at that amplitude position. So we just make sure we square it and then multiply by 1/2, and we'd find out 900 joules would be the total energy of the system. And that's typically the trickiness behind the questions they ask, is they'll give you a bunch of information and you have to discern how you can find the total at either the amplitudes where you would focus on the elastic potential energy, or at the equilibrium where you'd focus on the kinetic energy. So it just depends on what's given from problem to problem where you would need to focus. And that's the thing, like we're at that point of the year where it's all about creative problem solving. You really just can't memorize, oh, this is how you do this kind of problem, because they're going to give you an infinite range of different kind of questions, right? So you have to just get creative with how you can puzzle piece together your solution. Yeah, Ricky?
But it says amplitude is 3 meters, so that's just like implying that it's at 3 meters.
It doesn't even have to be at 3 meters at a given time. It's just saying when it's at the amplitude, the stretch is 3 meters. And so it's moving back and forth, but we know that when it's at that position, that would be the full stretch. And so that would be where the elastic potential energy is all there is, because it would stop when it reaches that point. So we don't even have to worry about, is it there right now? We're just saying when it's there, it wouldn't be moving. And so it would only have elastic potential energy when it's in that spot. Does that make sense? Okay. Questions? Other questions? All right, let's try another one. What is the maximum velocity of the mass in the mass spring system from the previous slide? And they give you some reminders here. The mass 2 kilograms, spring constant was 200 newtons per meter, and the amplitude of oscillation was 3 meters. So how would we go about finding the velocity when they are only giving us the same information they gave us before? Got an idea, Blake?
Shouldn't you do the total, which is 900 joules, is equal to 1/2 kx squared plus 1/2 mv squared? Just plug in all the numbers you have and solve for v squared.
Okay. So let me restate what you're saying to make sure I'm understanding. So you're thinking about like adding these two together and saying that is the 900?
Yeah.
Yeah, that's the idea. That's the concept here. And so if we take that a step further, what's going to be true about when it's at its maximum velocity?
There's going to be no elastic.
Right. So if we think about this relationship, the elastic plus the kinetic equals the total. We know the total's 900. And when the velocity is maximum, this is 0. So it's really just this that equals the 900 at that position. That making sense? I mean, it technically is the sum of these two, but the elastic's going to be 0 when it's at its maximum velocity. And so we can say, well, that 900 that we got before for our total is the maximum, it is the total. And because these two are equal in value when they're maximized, we know that that total 900 joules is also going to equal the 1/2 mv squared when it's only movement, when the spring is totally relaxed. And so we could find then the velocity is 30 meters per second. So while they only gave us information to directly find the elastic potential energy, we could find either that or the kinetic energy. And since we could find the kinetic energy, we could also find the velocity. So again, it's like I said, it's not that there's one kind of problem. They could ask you all kinds of problems. It's can you creatively come up with an idea on how you can piece together your knowledge base in such a way that allows you to answer a question maybe you've never seen before. That's the trick of College Board physics. All right. Last, looking at period frequency of a mass spring system. these equations, we've seen this one already. This was on our notes earlier today. That's what you're trying to figure out from your lab. And then here we're seeing the frequency, since period and frequency are reciprocal, we can just reciprocal this whole relationship. So if you want, in your lab report that's due Thursday, referring to these equations might help you sort of draw some conclusions, because this is the period and frequency of a spring oscillating system. Over here, it shows you how do they come up with this equation, and it's math, not magic. They're just saying, well, we know that the maximum amount of kinetic energy would be the same as the maximum amount of elastic potential. So all the kinetic energy it has when x is 0 equals all the potential energy it has when x is the amplitude. Okay, so that the maximums have to be equal. And so then when we simplify that mathematically, the 1/2 cancel, and then they've said, well, because it's moving in a periodic rhythm, it's like circular motion. So even though it doesn't really have a circular path, it's got that sinusoidal path. So if we think about circumference, instead of actually going in a circle, but 2 pi times the displacement, so you can see they actually make a note here that r is really just the displacement, but it's that sine cosine relationship. We could plug in the circumference divided by the period basically for velocity. Even though it's not technically moving in a circle, it's got that same circular pattern of rhythmic motion. And then the r becomes x, so then we have this solving for t. If we multiply both sides by the t squared and then isolate it, we end up coming up with this, just basically the algebra, kind of messy algebra to isolate the t. But that's where that equation comes from. So just again, I like to show you a lot of deriving equations, because as you're seeing more and more on your own tests, and you'll see in May, they often ask you to derive equations, and they want you to start with something you know, plug in other things you know, and come up with something new. Okay. In this case, they're just showing you how you're starting with energy that we understand, hopefully, simplifying a little bit of algebra, making a connection that circular motion and simple harmonic motion are mathematically virtually identical, and then solving for the variable. All right, and that gets us through everything I need to cover for simple harmonic motion. We've got it all complete. For what I would recommend for your assignment, I'm not going to actually, we'll save the FRQs for tomorrow, because we're going to have 80 minutes, and I don't want to, like I said, I want to start the new unit so while the seniors are all gone. So we'll do the FRQs tomorrow. We'll do one, then we'll do test corrections for a while, then maybe we'll finish up with one, just kind of have a little bit of break. I guess that'll be the flow. So for today, these last few minutes, we'll just give you a chance to make it not late to your next class on a Monday when the passing periods are so short. But I would recommend that we're kind of done with Unit 6 now. We'll review tomorrow, but I would recommend, I assigned for you to watch the first 4 videos. I'd highly recommend watch the other 4. It's not an assignment, but watch those videos, practice some of the questions on AP Classroom. I think that's a good way to make sure you're putting in your own time outside of class to review and really digest this information.
Also, for the video.